Here is a table from your book. You do need to know both of these names. They will not be provided for you. So you do need to know that. And this is really the best way to do it. Kind of number of electron pairs for central atom, number of bonds, and just make a table. We could add the one that's missing here from ours, which would be 3 electron pairs, trigonal planar, and 2 bonds would give us our angular. So we'll add that in there. But that's really the best way to do it. Is most people, myself included, can't really think about what things look like sort of in 3-dimensional space, just to do it based on number of electron pairs, number of bonds, and that's sort of the easiest way to do it. Now, again, remember that double bonds, triple bonds count as both 1 electron pair and 1 bond when you're doing geometry only, and that's an important thing to keep in mind. So let's take a look at maybe some of the ones that we saw previously, or actually that we actually drew. I think we did this guy on that example. I think we did this guy. We did this guy. We did or just did a second ago as well. I think we had this guy. So this is the one I think from the previous example we did earlier. And if we wanted to do geometry of each of these guys, why don't you take a moment and do both the electron pair geometry and molecular geometry for each of these guys and see what you come up with. Okay, so let's take a look here. So really, this one should be the simplest. Only 2, which is diatomic molecules, which means the geometry is going to be linear. There really is no central atom. And remember that this chart that we're looking at here and that we talked about is really when you have 3 or more atoms. That's where you want to use this chart. All right, so this one we do have 3 or more atoms. If we go to the central atom here, that is 1 electron pair, 2 electron pairs, 3 electron pairs, 4 electron pairs. So that takes us into one of these regions. In terms of bonds, it has 1 and 2 bonds. So that is here. So the electron pair name should be tetrahedral. The molecular geometry name would be bent or V-shaped in this case. We take a look at the next one, which is CO2. Central atom is right there. Remember that double bond counts as only 1 electron pair and 2 electron pairs, which takes us to here. And also in terms of bonds, that counts as 1 bond. This counts as 1 bond. So that has 2 electron pairs and 2 bonds. That is right here. That is going to give us, for this guy, an electron pair geometry name of linear and a molecular geometry name of linear as well. Coming to here, this is the guy we did earlier. In this molecular geometry, it has, again, 1, 2, and 3 electron pairs. Also has 1 and 2 bonds. That's going to be our trigonal planar for electron pair geometry and our angular. Lastly here, looking at our nitrogen, has 1 electron pair, 2 electron pairs, 3 electron pairs, 4 electron pairs. That's going to bring us to one of these guys. And in terms of bonds, it actually has 4 bonds, which would bring us here. That means that the electron pair name will be tetrahedral. And our molecular geometry name will also be tetrahedral. So this is how you can do your geometry for these things, by looking at the central atom and basically determining how many electron pairs and how many bonds there are. Now you can see in our example here, dots on the central atom, different names. No dots on the central atom, same name. No dots on the central atom, same name. Again, dots on the central atom, different names, right? So different names for something that has dots on the central atom, and again, same name if they have no dots on the central atom. All right, so I want to look at one last thing here in terms of geometry just to show you. I'm going to kind of erase it and clear it out so we can see. Let's say we had something not like that. Let's say we had something, let's see that there. Let's say we actually had something like this here. Now, in this particular case, we actually have a molecule kind of like, and actually, let me draw that one as well. Get something to draw that one with. And what I'm talking about is our nitric acid that we drew earlier. Well, okay, so both of these guys actually have two central atoms. For the case of the first guy, it's the carbon and the oxygen, and here is the carbon or the nitrogen and the oxygen. When you have a molecule that has more than one central atom, you can actually do geometry for each central atom separately. So for example, for the first one here, we would do it for the carbon. We basically would put our hand over where I just kind of boxed in green there, and we would look at just the carbon here. And the carbon has 4 electron pairs. And this guy does count for the carbon as well. And it has, in terms of bonds, it has 4 bonds, right? So for the carbon, it actually has 4 electron pairs and 4 bonds. The molecular geometry of this guy would be tetrahedral. Now what we would do is we would then go back and look at just the oxygen side as the central atom. So we'll go back now and kind of put our box going this way. And we would still count, though, this line for the oxygen as well, because they are sharing that. So in terms of the oxygen here, it has 1 electron pair, 2 electron pairs, 3 electron pairs, 4 electron pairs. So the oxygen has 4 electron pairs. And it has 1 bond. And once again, this bond would also count for the oxygen, 2 bonds. Which means for the oxygen, its molecular geometry is actually bent or V-shaped, which is what we got down here. So you would do the geometry for each central atom separate from each other by kind of putting your hand over one half of the molecule and then switch it and put it over the other. So we would kind of do the same thing here. We would kind of put our hand to the right, for example, to start with. And when we look at the nitrogen, it has 1 electron pair, double bond counts as 1, and 3 electron pairs, and has 1, 2, 3 bonds. So the molecular geometry for our nitrogen in that case is something with 3 electron pairs and 3 bonds. That's going to give us a trigonal planar geometry. Now we're going to look at the oxygen side. The oxygen has, once again, 1 electron pair, 2 electron pairs, 3 electron pairs, and we still have to count that bond coming into the oxygen from the outside. And that's going to be 4 electron pairs. And it has, in terms of bonds, 1 bond there. And again, counting that guy on the outside coming in, 2 bonds. Which means the geometry here, the molecular geometry for the oxygen would also be bent or V-shaped. So if you find yourself with something that you drew that has more than one central atom, basically just put your hand over one part of the molecule and look at the central atom by itself. You still count the bonds and the electrons coming in, and then flip it around, put your hand on the other side and count the other central atom. Same thing, still counting the electrons and the bonds coming in. All right, the last thing we're going to talk about is molecular polarity. And do you want to make a distinction between 2 types of polarity that we've been talking about, or that we've talked about before? We have bond polarity. And that is represented with those little bond dipole arrows where it points to a more negative side, a more positive side. And we oftentimes use the difference in electronegativity like we did earlier in the chapter. When we have a dipole moment, this is really talking about molecular polarity. And that is the entire molecule as a whole is the entire molecule as a whole sharing electrons equally or unequally? And that's different than bond polarity, where we look at electronegativity and it's just between these two atoms in the bond in this molecule, or in this particular bond between these two atoms. Are the electrons being shared equally or non-equally? So if you do have a dipole moment, that is usually accompany a polar molecule, which means overall, when you look at a molecule that is polar, there's a side that's more positive and a side that's more negative. If you do not have a dipole moment, so guys that do not possess a dipole moment, those are non-polar molecules, which essentially means overall the electrons in that molecule are being shared equally. Kind of no charge happening in that particular molecule. There's not a side that's more positive. There's not a side that's more negative. So they are two different things. And really the only place where bond polarity and molecular polarity are essentially the same thing is when you're dealing with diatomic molecules. So when you're dealing with diatomic molecules, both the bond polarity and the molecular polarity will be the same. What do I mean by that? Well, for example, if I look at hydrogen, H2, we already know that the difference in electronegativity here, right, in this case, if we looked up the values, is 2.1 minus 2.1, which is 0. That tells us that the bond between H and H is a nonpolar bond. Now, because in H2, the only bond in the entire molecule is that one bond, and because that one bond is nonpolar, that would mean that this would also be a nonpolar molecule. Because frankly, there's just one bond present, and that one bond's nonpolar. You know, same thing if you had a double bond, it has no effect on it. The difference in electronegativity here is going to be 0. And because that is the only bond there, that is both a non-polar bond. And because that's the only bond present, that would make this a non-polar molecule. Now, if you have something like HF, for example, we already know that the difference in electronegativity between these two guys, by the way, if you do it, as we saw, I think was 1.9, that is a polar bond where fluorine is more negative, hydrogen is more positive. We could draw our arrow heading in this direction. So this does have a polar bond. And because this is the only bond present, it would also be a polar molecule, where that arrow that I drew up on top would be the dipole moment, right? And also the bond dipole. But in this case, this would be the dipole moment. And it tells us that the fluorine side of that molecule is more negative than the hydrogen side because overall electrons are over there. So the easiest one to determine whether or not a molecule is polar or non-polar is when you're dealing with diatomic molecules, because they have only one bond present. If that bond is non-polar, then the molecule will be non-polar. And if that bond is polar, then the molecule will be polar. Gets a little bit more difficult when you're dealing with 3 or more atoms. And when you're dealing with 3 or more atoms, you need to look at 2 things. First off, is there polar bond? If there are polar bonds, then you need to go to the second thing. And if there are not polar bonds, then the molecule is going to be nonpolar. And if there are polar bonds, yes, then you're going to go to number 2. You have to look at the molecular geometry. So you have to look at that molecular geometry of it. So for example, if we look at our friend there, carbon dioxide that we saw earlier, between carbon and oxygen, which are in the same period of the periodic table, we know that that's going to create a polar bond with the arrow pointing towards the oxygen being more electronegative. Also, we'll have a polar bond this way. So carbon dioxide does, yes, have polar bonds. So you may think to yourself, all right, well, then it's got to be a polar molecule. But we do need to look at the geometry here. And the geometry, the molecular geometry is, again, 2 electron pairs and 2 bonds, which means the geometry here is linear, basically a straight line. So because of the geometry here, we basically have oxygen pulling this way. We have oxygen pulling this way. And if you can see it, I don't know, but my pen is not really going anywhere because they're pulling in opposite directions. So in this case, because of the geometry, they actually cancel each other out. And this guy is actually a non-polar molecule. And this is a really good example that you could have polar bonds within a molecule, but because of the geometry that's present, it will actually be a non-polar molecule. And that is because these bond dipoles that we draw up here, these are vectors. And vectors have direction and have magnitude. Then I fell asleep in physics, but I woke up long enough to know in certain cases, they will cancel each other out. And in certain cases, they will actually add to each other. This is a case that they will cancel each other out. Now, if we take something like water, water also has polar bonds heading towards oxygen in this direction. So it does have polar bonds. The geometry here, as we saw, and again, the molecular geometry here is bent or V-shaped. So in this case, we have basically our polar bonds coming together towards the top. Kind of think of it like a string. You could pull the string up, the entire molecule will move. They actually will add to one another in this case, and we will get a net dipole moment heading in this way, where the oxygen side of water is more positive, hydrogen side is more negative. How does that really work? Well, if you do a little vector adding, you kind of take the vector like this, head to tail, I think. Add the other one to the end of it, and before you know it, they add together, and you get that way. So in terms of the sort of bond dipole arrows, which are really vectors, if you have a situation where they are heading directly at each other in equal and opposite directions, are directly opposite of each other in equal and opposite directions, they will cancel out to each other. Where they don't really head directly at each other in equal and opposite directions, they can add to each other like we see here in water. Frankly speaking, nobody wants to draw vectors and figure it out that way. So there must be an easier way to do it. And the answer is there is. So there are certain geometries which are referred to as being symmetrical geometries. And these are geometries, and these are molecular geometries, by the way, where if we take something in our case here, you guys have trigonal planar and tetrahedral. And what both of these molecular geometries have in common are no dots on the central atom. They're all bonding electrons. So if you have one of these two molecular geometries on your Lewis structure with no dots, and everything on the outside atoms are the same atoms, it most likely will be a non-polar molecule. They will all be basically equal and opposites of each other, and they will cancel each other out. So for example, if I take something like this, and I'm not going to draw all the dots here, just going to draw really quick. So if I look at the central atom, I have no dots. Everything on the outside is the same. This is going to be a non-polar molecule. That's because we do have polar bonds all heading towards the fluorine, but because they're all equal and opposite of each other in terms of where their location is, you could think of it like a tug of war. Everybody's pulling that string equally and opposite of each other, which means it's not going to go anywhere. They're all going to cancel each other out. So although this does again have polar bonds, because of the geometry here, this will be a non-polar molecule, even though it does have polar bonds. What happens though if I swap out one of those fluorines for a hydrogen in this case? Still have polar bonds heading this way and this way. Carbon and hydrogen is actually a non-polar bond, slightly heading towards carbon, but really non-polar. So what happens in this case though is you got three of these guys, like on the tug of war type of thing, pulling in one direction, and this guy over here is not really pulling in the opposite direction. He's actually pulling a little bit with them. And you're going to kind of think about the whole rope's going to move, the molecule is going to move if that's like a rope, and it will now become a polar molecule. So that's the exception. So if you have a Lewis structure that you draw that's one of these two geometries, basically no dots on the central atom and everything on the outside is the same element, it will be a nonpolar molecule. But if you draw a Lewis structure and you have no dots on the central atom, you have one of these two geometries and everybody on the outside is not the same element. Like we have on the right here, we have a hydrogen and some fluorines on the outside. It most likely will then become a polar molecule. That leaves us the other types of geometries, which are unsymmetrical. And these unsymmetrical geometries, for your cases, is your angular, your trigonal pyramid, your bent, are V-shaped. And once again, these are molecular geometries. What all these have in common is there's dots on the central atom. And if all the outside atoms are the same, then it's going to be a polar molecule. So how does that work? Well, we can look at our water, for example, as an example of that. I see dots on the central atom. These guys are the same, going to be polar. So that's an example of that. So that pretty much leaves you only one thing that you have to worry about, which is the geometry of linear. And because it's a straight line, if you have the polar bonds going in opposite directions or heading right at each other, then it will be a nonpolar molecule. But it is possible that you could have in a linear situation, for example, all the polar bonds heading in the same direction. And if that was a linear geometry and they're all heading to the right there, then it would be a polar molecule. So that's something to keep in mind. But since linear is a straight line, it's pretty simple to figure out. This is probably the best way, again, just to go dots or no dots to figure it out. So if we drew up some of the ones that we looked at, previously along the way today, do a little bit of this. We had this. We have this, I think. We had this. See, we have that. Yeah, we'll take a look at some other ones that we saw along the way too. I think we saw this guy. Good. I think what was that one that we had there? I believe that'll work. All right. So why don't you take a moment here and determine are these guys polar or non-polar molecules? So again, we're looking at the molecular polarity here. So take a moment and determine. Okay, let's take a look and see. I had a couple more there at the end. So if you want to take a moment, you can stop and do those as well before we get going. But let's take a look real quick, and this is pretty much as fast as you could do it and probably still get the right answer in most cases, or more than most cases. So here we go. I'm going to look at this one, and this is what I should be thinking. We got diatomic molecule. First off, in terms of polarity, that is a nonpolar bond, which means that this molecule is going to be nonpolar because that's the only bond present. Here I had got 3 or more. I need to look at the central atom, always the central atom. I see dots. I see these guys are the same. That means polar molecule. I look at the central atom. I got 3 or more. I see no dots. Everybody on the outside is the same. Based on geometry, this is going to be nonpolar. I look at the central atom. We got 3 or more atoms, no dots. Everybody on the outside is the same. Going to be nonpolar. I look over here, I see dots. Everybody on the outside is the same. Going to be polar, this molecule. I come here, I see no dots. Everybody on the outside is not the same. And it does have a polar bond going in that direction, which means this is going to be polar in this case. I come here, everybody's the same on the outside. I see no dots. And by the way, this has no polar bonds to begin with because carbon and hydrogen is non-polar. And that means that this is going to be nonpolar. Once again, there are polar bonds heading here. And also same thing here. These are polar bonds heading towards the nitrogen in this case. And also, again, polar bonds heading here towards the oxygens and our polar bonds heading towards here. Now, in terms of dipole moment, once again, if you had to sort of draw where the dipole moment would be, in this case, it would be heading towards the chlorine. It would be heading actually towards the nitrogen in this case. With the nitrogen being more electronegative. And this would have none. This would have none. This guy, again, would be heading towards the sulfur, this guess. So that's how quick you can determine whether or not a molecule is polar or nonpolar. And again, that is molecular polarity, not to be confused with bond polarity, where we look at the difference in electronegativity values. Once again, the only place that bond polarity, differences in electronegativity values, and molecular polarity basically cross over is like the very first example here in a diatomic situation. So they are two different things, and you want to make sure you kind of keep them separate of what we're talking about. So molecular polarity as a whole, is that molecule have equal sharing of electrons? Is there a negative side or a positive side? And obviously bond polarity is specifically talking about between two atoms. Are the electrons going to be shared equally or unequally? And that's what we see here again with our CO2. And that's why the geometry is really important, because if the geometry of the molecule was different in CO2, like it was bent or V-shaped, then it would be a polar molecule. But once again, it is not the geometry. The geometry is linear. And that's why when we do have 3 or more atoms involved, you do have to take that molecular geometry into account. All right, that is part 2 of chapter 11, a little Lewis structure drawing action, some molecular geometry, and some polarity, molecular polarity happening. I hope you've enjoyed part 2 here. We'll see you on the next one. I'm going with maybe the next chapter. We will talk about whatever that may be. Have a good night, evening, or morning. I'll see you next time. Bye-bye.
Hello, and I hope you've enjoyed this lecture on chemical bonding. Let us finish it like we usually do with a chemistry joke. Let me think of one here. Ah, yes, let's try this one and see how it does. Why didn't the physics and biology teachers get along? They didn't have chemistry.